Hello. Okay, so let us begin this module, Living with Mathematics, for this semester 1 of academic year 2019 to 20. And I presume you are all from various diverse backgrounds. I am from the Department of Mathematics, and I am going to tell you how it is to live with mathematics. Although all of you are from various different and diverse backgrounds, the pitch of this module and the module content would be, I'll try to make it such that all of you, it is easily accessible to all of you. And given the timing of the lectures, which is, basically after hours, I'll try to make it technically as light as possible, okay? Not very taxing. Okay, so just a bit about the practicalities of the module. So the grading policy is that there will be 30% homework, and I'll try to make the homework submission towards the later part of the semester so that you have ample time to work on the homework. And the final exam will be 70% and help sheet will be allowed, okay? All lectures will be webcasted in order to answer some of your questions. However, I would encourage you and I would request you to attend the lectures, because watching the webcast and watching the lectures directly being there in the lecture auditorium it's not exactly the same thing. You get more out of being in the auditorium when the lectures are happening. And please feel free and please try to give me feedbacks about the course. I'm sorry? Sure, because if I had attendance, then I would not put this line about encouragement. No, so the homework questions would be similar to the final exam questions, which is like MCQ. Any other questions? Any other questions? Okay, so let us now begin in true earnest about living with mathematics. And today is the first lecture, and today we are going to begin from a topic which on one hand depends quite a lot on mathematics, but on the other hand is very important and useful for us in the modern society, namely money and personal finances. It's important to all of us and it involves a lot of mathematics, so that's the first topic we are going to tackle. Just a bit more on the generalities about the reference books for the course. So there is this book called Living with Mathematics by Yu Kyung Leong. Then there's a book by Hay called Mathematics on Everyday Life, and so on. Slides and tutorials will be posted on Luminous, and there will be weekly tutorials starting from week 3 as usual. Okay? So let me try to summarize from a very high level, from a broad perspective, what are the objectives of this module. So the objective, our objective in this module is to share with you the experience of living with mathematics. So we would like to exhibit some simple mathematical ideas applicable in everyday life, and in the process we want to gain an appreciation of the beauty and the power of mathematics. So the topics will be chosen from various diverse areas where mathematics is very useful for us in our day-to-day life. So so the topics would be chosen from a list that includes personal finances and money, a topic that we will address head-on today itself. Then there is the topic of language of mathematics, mathematics in social and political sciences, the mathematics of counting. Well, counting is almost the same as mathematics. Then the mathematics of graphs, that of management and logistics, a bit of probability and statistics, which is becoming very important these days, and which is also my own concentration area, my focus for my own research. And then mathematics of coding, error correction, and encryption, which is also very important nowadays. Okay? So let us begin with lecture 1 proper. So our motivating example is the following. So suppose I put $100 in a bank at 5% annual interest. Okay? So this is the condition that is laid out to me at the time when I open my savings account, so that I will have 5% annual interest. And my question, the natural question to ask is that how much money will I have if this arrangement holds for a certain number of years? So generally we will plan for 5 years, 10 years, 20 years nowadays is already seems like an age. But for simplicity, in the first lecture, let us think of 100 years. Okay? So if I put $100 in a bank at 5% annual interest, then how much do I expect to have after 100 years? So we will do some simple mathematics in order to understand, how this question, how to answer this question. And the first aspect of mathematics where this simple question leads us to is the issue of precision. Mathematics is an exact science. You have to be very precise. So there is no room, there is no scope for ambiguities in mathematics. So in particular, in the question that we have here, suppose we put $100 in a bank at 5% annual interest, how much do I have after 100 years? So there, of course, there are several ingredients to this question. One is the initial deposit. One is the total number of years. These two are laid down to us pretty clearly, $100 and 100 years. However, the other crucial ingredient to this question is the question of annual interest. So the annual interest, we are told, is 5%. And herein lies the ambiguity of the question, because annual interest might mean several different kinds of annual interest. And usually when you are handed down these kind of documents by the bank, your elders, your advisors, they will advise you to read carefully the fine print, because it is the fine print of your agreement which will explain to you exactly what kind of annual interest you will be getting from the bank, and the exact nature of the kind of annual interest which you will be getting from the bank will have a big impact on how much money you can expect to have after 100 years. So in other words, the exact nature of this 5% annual interest which is contained in that fine print will be crucial to determine the answer to this question. Okay? So, so some of you might already have some familiarity with the different kinds of interest. So in general, there are various different kinds of interest, like simple interest or compound interest. Okay? So what is simple interest? So simple interest is basically what it sounds like. It's simple. So the calculations are also very simple. So simple interest means that you just have this $100, 5% of $100 is $5, and it's simple, so there is no further complication. So you will just be getting this 5%, that is $5 every year. And if you keep on getting that for 100 years, you get 5% every year for 100 years, so in total you get $500, okay? And initially you had $100 to begin with, so with the additional $500, you will have $600 in total. So that's simple interest. And the fact that it's simple is encapsulated by the fact that our entire exercise took just a few lines of calculation. But in real life, life is really simple. So simple interest is seldom used. It is rarely used because the idea is that suppose you start with $100 at 5% annual interest. After the first year, you get $5 additional from the bank. So after 1 year, you have $105. If you have $105 after 1 year, then when you go on to the next year, your 5% annual, so your entire money is already deposited with the bank. So the bank already has your $100, plus it also has a $5 which is actually yours. So the bank is doing its business on the basis of this total $105. So to be honest, the bank should pay you 5% interest. In the second year, the bank should pay you 5% interest, not only on the $100 you gave them initially, but the 5% interest should be calculated on the additional $5, so in total $105, which the bank actually has in possession and which actually belongs to you. So if you have, so here is a simple calculation. So if you have $S as the start of the year, then at the end of the year, you will have 1.05 times $S. Why is that? Because at the end of the year, you will have $S plus the interest. So this is $S plus what is the amount of interest? It is 5% of $S, and 5% of S is just 5 over 100 times S. So this is S plus 0.5 S. So this is 1.05 S, which is exactly what we have here. So if you start the year with $S, then at 5% annual interest at the end of the year, you will end up with 1.05 times $S. Okay? So that's something very crucial. And this is in some sense the fundamental equation of dealing with compound interest. Once you understand this equation lies at the heart of everything. So once you understand this, you are good to go and you can calculate anything about compound interest that you like. For example, so in the beginning, in our original problem, you began with $100. So after 1 year, you have 1.05 times $100, which is $105. Now you are starting the second year with $105. So at the end of the second year, you will have 1.05 times the 105 you started with. So this is 1.05 squared times $100, because 105 was already 1.05 times 100, and you have another factor of 1.05 here, so this is 1.05 squared times $100. So you are starting the third year with this, and with this amount of money. So this is your S at the beginning of the third year. So now, just let me erase a moment. Oops. Okay, so let me just write this equation, 1.05 times $S, okay. So At the beginning of the third year, you are starting the year with 1.05 squared times 100. So this is your S at the beginning of the third year. So at the end of the third year, you will have 1.05 times this value, right? So this is after 3 years. Get 1.05 times $100 cubed, because now we have this factor of 1.05 multiplied 3 times. And if you go on, then at the end of 100 years, so after 3 years, you have 1.05 to the power of 3 times $100. So if you go on, you can see that the year is basically appearing as the index of this power of 1.05. So after 100 years, you will simply have 1.05 to the power of 100 times $100. Okay? So this is, if you do the calculation, it will turn out to be 13,150.13. Of course, this is a toy example because none of us really are expecting to live for 100 years, but really it tells you the power of this simple math and this simple equation. And from now on, interests will always mean compound interest, because in real life banking and finance, that's the kind of interest that you deal with. Any questions? So this is annually. You can also do it monthly, but you know the main idea will be the same. So you have to take into account how the money changes at the end of every month. Instead, so here we are accounting for how the money changes at the end of every year, right? And doing the calculation. If you are interested in, or if you are looking into a situation where your money is being compounded monthly, then instead of calculating how the money is accumulating at the end of every year, you have to do the calculation with accounting for how the money increases and at the end of every month. But the main idea is the same. See, that's the power of mathematics, because there is one simple idea, one simple equation at the heart of it. And once you understand that equation and how to use it, you can take that idea and apply this kind of calculation to many different settings, which are variations of the same thing. Okay? Okay. So now let's pretend to be very mathematical and state the calculation we just discussed in a kind of a serious looking fashion. So we will call it a proposition. We will call it the proposition of the day, and the proposition of the day is as follows. If you invest $0, which is our starting capital, so C0 for us was 100, then with an annual compound interest rate of alpha, so alpha was 5%, which is 0.05 in the previous example. At the end of n years, you will have 1 plus alpha to the n power of n times C0 dollars. And the idea is very simple. It's the same idea essentially. So you started with C0. So this is your principal plus, so at the end of 1 year, you will have C0 plus the interest in 1 year, which is C0 plus 0.05 in the previous case, C0. So 0.05 for us is alpha. So we will generally call it alpha. So this is C0 plus alpha times C0. So this is the amount at the end of 1 year, because alpha is the compound interest rate. So this is 1 plus alpha times C0. So at the end of 2 years, you will get 1 plus alpha squared times C0 and so on. So at the end of n years, you will get 1 plus alpha to the power of n times C0. So it's just the same idea, the same calculation written with symbols in a formal manner. So there are 4 parameters in the proposition. So the initial capital C0, the final amount of money you get, which is Cn, the number of years, which is n, and the compound interest rate, which is alpha. So this is kind of a more formal statement of the basic equation that lies at the heart of the matter that we just learnt about in the previous slide. And usually the questions will involve the following. So there are 4 items, there are 4 variables in this equation. Usually you will be given, in a word problem, you will be given in one way or the other, you will be supplied with information on 3 of these parameters, and you will have to calculate the 4th parameter from this equation. That's usually how it goes. Okay? So let's take the first variation of this problem. So when will your fortune double in the above scenario? So every year I am getting a compound annual interest rate of alpha. When will my initial seed money become double? So, for this question, it might be tricky because I am not telling you how much money I am investing to begin with. But that's just a trick, because once you sort of use the fundamental equation and figure out how to do the calculation, you will see that the number of years actually will not depend on how much money you put in. Okay? So let us assume that we are starting with C0 amount of money, and I will get a compound interest rate of alpha annually, and after n years I will have 2 C0 dollars. Okay? So in other words, after n years I will have Cn amount of money, Cn dollars of money, where Cn is 2 C0. Okay? Because my money has doubled from C0 to 2 C0. So let's recall the fundamental equation. Cn is 1 plus alpha to the n C0. And just to sort of make sure that every one of you is on board with me, let us go over the details of how we did this calculation in the first place. So in the beginning you have C0 dollars. After 1 year you have C0 plus the interest you get in 1 year. So this is C0 plus in 1 year you get compound interest rate of alpha. So this is alpha times C0, right? Alpha times C0 is the interest. And then after 2 years, so you start the second year with C0 plus alpha times C0 that you had from the first year, and then you get the interest. So what is the interest now? So you started with C0 plus alpha times C0. So you can write C0 times alpha times C0 as 1 plus alpha times C0. So you started here with 1 plus alpha times C0. So after you start the second year with 1 plus alpha times C0, and you get the interest in the second year. So what is your total? So your initial money at the beginning of the second year was 1 plus alpha times C0 here, and your interest is just alpha times your initial money at the start of the second year. So this is alpha times 1 plus alpha times C0. And what you can do is that you can notice that 1 plus alpha times C0 is common between the two terms. So you factor that out, so you get 1 plus alpha times C0 times 1 plus alpha, right? Which is simply 1 plus alpha square times C0. Okay? So after 2 years, you get 1 plus alpha square times C0. So you notice that the year is always appearing at the exponent. So after the end of n years, you will get you will have total amount of money Cn, which is 1 plus alpha to the power of n times C0. So n just appears on the exponent of 1 plus alpha. Okay? So just to remind you, to refresh you, this is how we arrived here. So here in variation 1, we are interested in at what time the fortune will double. So the fortune doubles in, let's say we start with amount C0, interest rate is alpha, and in n years my money should be Cn, but I want to find n such that Cn, the amount of money I have, is twice what I originally had. So Cn is twice C0. So let's now apply the master equation. So let's say, let's use this, use Cn equal to 1 plus alpha to the n times C0 with Cn equal to 2C0. Once you put this in the fundamental equation, you get 1 plus alpha to the n times C0 is 2C0. So now C0, C0 cancels, and 1 plus alpha to the n, so we are left with 1 plus alpha to the n equal to 2. So now you take log, so this is n log 1 plus alpha equal to log 2. I mean, log, we will be taking log to the base e, so we denote it by ln. Okay. So we want to understand this. So we imagine that alpha is given to us. So alpha is something like 0.05. So we really want to find a numerical value of n. But usually, you know, banks are not going to give you that much interest. So alpha is usually not very high, not very large. Alpha is usually pretty small, like 0.05 in the example that we saw at the beginning of the lecture. If alpha is 0.05, then we can use an approximation. So if alpha is very small, we can use an approximation. So the only complicating factor here is this log term, because the log is not such a nice function. It's not so easy to work with using, you know, if you want to just do some calculation with it. So the approximation is that if x is small, then log of 1 plus x that we have here is you can approximate it by x. So in particular, if alpha was something like 0.05, which is very small, you can say that, well, you know, you have this complicated equation involving logarithms here, but at least one log I can get rid of by using the approximation that log of 1 plus 0.05 is basically 0.05 itself, because when x is small, log of 1 plus x is approximately x. Okay? So this is a math fact, and hopefully we will have the occasion to sort of go over the details later. So let us use this approximation here. So let us substitute this by alpha. So this is n times alpha equal to log 2. So then this implies that alpha equal to log 2 over n, or rather n equal to log 2 over alpha, which is the form in which we need it. So if n equal to log 2 over alpha, so if n equal to log 2 over alpha, you can think of, so alpha is something like 0.05 if the interest rate is 5%. So for convenience of calculations, often banks usually give us the interest rate in terms of percentages rather than a fraction like 0.05. So the bank will rather tell you 5% instead of telling you 0.05, right? So let us say alpha is just beta percent. So if alpha was 0.05, then beta percent is just 5%, right? Beta will be just 5. So let's do the calculation in the form that the banks usually give us the data, and then you can see that n will be roughly log 2 over alpha, which is log 2 over, so alpha will be equal to beta by 100 if you express it in the percentage form. So n, so if you replace this by beta by 100, then this is 100 log 2 over beta, and you can look up any math table or your calculator to see what is the value of log 2, and the value of log 2 is 0.693 blah blah blah. So you put that in here and you get 69.3 over beta. Okay? So 69.3 is not a nice number. 72 is a nice one. Don't ask me why not 70. 72 is a nice number. Okay? So we will round 69.3 to 72, and 72 has the benefit of having many factors, and roughly we will say that we will state the rule of 72, which means the following: at an annual compound interest rate of beta percent, it will take about 72 over beta years for an investment to double. Okay? And you can, and this is a basic idea of dealing with compound interest. So you can, instead of investment, you can think of debt, because the relationship between your bank and yourself is basically the reverse of the relationship between you and the person whom you owe your debt to, right? So basically it's always the same idea, and you can use this rule of 72 to find when at what time, after how many years, your investment or debt will double. And for those who are still wondering a bit about this 72, let me point out a simple thing to you. So 72, as we already mentioned, has many factors. So one of those factors is 12, and there are 12 months in a year, right? So it's beneficial to work with something with a number which is a multiple of 12, because because you are, on one hand, you will be dealing with 12 months. So it's good if things are divisible by 12. Okay? Any questions? Okay. So let us go a bit further, and let us instead discuss a bit about certain things which are a bit mathy on one hand, and on the other hand, they might seem a bit unrelated to what we were discussing until now, but in fact they are related. So, we will discuss linear versus exponential growth. So linear growth is when you plot your investment against time, you get a straight line. Okay? So if you will get a straight line, like this. So this intercept is A, and this slope is B. Right? Whereas exponential is something like this. It's a curve like this, increasing very fast. So at t equal to 0, this is A. So you are starting with the same amount of money, and then you are increasing very fast like this. So if you plot them on the same curve, you will get, if you combine the two curves, you will get something like this. Okay? So we noted in the calculations before that if you put your money in the bank for 100 years and you are getting 5% annual interest, then if you had simple interest, you would end up having $600 after 100 years. If you had the same level of compound interest, then you will have, then you will have much bigger amount of money, $13,000 at the end of 100 years. So And this is kind of explained by the fact that that when you are doing simple interest, your the curve of your money against your time, the number of years you put the money, is linear. So it's something like this. Whereas in the case where it's compound interest, your curve will be an exponential curve like this. So the math fact is that exponential growth is much faster than linear growth, which explains that after 100 years, you will have much bigger amount of money if you have compound interest rather than simple interest, which is basically a real life reflection of the fact that an exponential curve grows much faster than a linear curve. So you start with C0 amount of money here. The slope is your compound interest, or rather, the slope is the value of your annual interest. If you are simple interest, you are growing like this. If you are compound interest, you are basically growing like this, steeply. So after 100 years, which is a long way away down this road, the two friends have diverged a long way from each other. That explains the difference between $600 for simple interest and $13,000 for compound interest. Okay? Any questions? So, variation 2 on the same theme is to discuss semi-annual or quarterly rates of interest. So, sometimes interest rates are presented as monthly or quarterly or semi-annual basis. So, for example, consider a loan of amount C with an interest rate of 2% compounded quarterly. How much do you owe after 1 year? So, the wrong way to look at it is that you are having 2% interest every quarter. There are 4 quarters in the year. So, the total interest you accrue in the year is 2% for each quarter. So, 4 times 2, so 8% in total. That's the wrong way to sort of look at it. The right way to look at it is to apply our same simple logic, same fundamental equation of compound interest to this particular case. What is that? So, if you start with, at the end of the first quarter, you start with C in the first quarter, and you have 2% compounded quarterly. So, at the end of the first quarter, you have C plus 0.2 C. So, this is 1.02, so this is 0.02 C. So, this is 1.02 C amount of money at the end of the first quarter. This is what you begin the second quarter with. So, at the end of this, and you get 2% interest for that quarter. So, at the end of the second quarter, you get 1.02 C plus 0.02 times 1.02 C. So, this is 1.02 square times C. So, this is at the end of the second quarter. At the end of the third quarter, you will get 1.02 cubed times C. Just apply the same logic once again. So, at the end of the fourth quarter, which is at the end of the year, you will get 1.02 to the power of 4 times C. And you can calculate 1.02 times 4, that is 1.0824. So, the amount of money you owe is 1.0824 times C instead of 1.08 times C. So, actually taking into the fact that you have compound interest compounded quarterly gives you a much bigger value of the loan that you need to pay back. Okay. So, and if you convert this into percentage, you will see that the interest rate that you are having to pay is the total amount of interest that you are having to pay in a year is basically 8.24% of C, because the interest that you pay at the end of the year is this 1.0824 times C, this is the total, minus C, so this is 0.0824 C. Okay? So this is basically, oops, sorry. So this is basically 8.24% of C. So this rate, which is 8.24% in our case, is called the annual percentage rate, or APR for the loan. So 2% compounded quarterly is not 4 times to 8%, but so the APR is not 4 times to 8%, but the APR is actually 8.24% because of the calculations we just did. Okay? Any questions? So, let's switch gears and let's move on from yearly to monthly rates. So if a loan has an annual interest rate of I, what is the monthly rate alpha? So this is exactly sort of trying to switch back between monthly interest rates and yearly interest rate. So if you have compound interest, if you have a monthly rate of alpha, then if you start with amount C0 at the beginning of the first month, at the end of 1 year, you have a monthly rate of alpha, so this is, and there are 12 months in a year, so at the end of 1 year, you have 1 plus alpha to the power of 12 times C0 amount of money. Okay? And this, but if the annual interest rate is I, then at the end of 1 year, you will get 1 plus I times C0 amount of money. So I and alpha should be such that you should be able to equate these two amounts of money, because these are nothing but two expressions for the same amount of money you have after 1 year. So this would force us to have the equation 1 plus alpha to the power of 12 equal to 1 plus I. So in other words, 1 plus alpha equal to 1 plus I to the power of 1 by 12. Okay? And essentially, in the previous slide we saw that it is wrong, it's dangerous to sort of take the quarterly or monthly interest rate and just multiply that by the number of quarters or the number of months. So similarly, if you take the monthly interest rate and just sort of linearly extrapolate it and multiply by the number of months, you are going to get into trouble. So basically, this is the content of this formula. Okay? So if the annual interest rate is I and the monthly interest rate is alpha, then they are related by this kind of equation. Okay? But you see, although the equations might look fancy or having complicated powers like the power of 1 by 12, at the heart of it lies a very simple mathematical idea, which is driving all these equations together. And that's what I want to sort of highlight and focus on in this module. Okay? Any questions? So, okay, so here is a natural investment example. So you are given two options: invest $1,000 now, or take $1,100 in 2 years' time. So, so you want to understand what is the annual rate of investment or annual rate of investment returns that would make the first option more attractive. So if you invest now, you accrue certain amount of money every month or every year, and after 2 years you will have a certain amount of money. When will that money obtained from investment exceed $1,100? That's when you would want to invest money now. So that depends on the rate of investment return that they are giving you, and basically you can calculate this rate of investment return using this kind of equation, because if you invest $1,000 now, the annual compound interest rate is alpha, then after 2 years, as we already saw, it's 1 plus alpha squared times C0. C0 here is $1,000 that we are investing now. So after 2 years, you will have 1 plus alpha squared times C0, I mean 1 plus alpha squared times 1,000. So you want that amount after 2 years to be bigger than 1100. That's when it will make sense for you to invest. And you can solve this equation and get alpha has to be bigger than 4.88%. So you read the fine print of what the bank hands you, and if the annual interest rate is bigger than or equal to 4.88%, then go ahead and invest. Okay? So here is another variation from future value to present value, but I think for the first lecture and the first half of the first lecture, we have had a lot of discussion, so maybe this is a good point of time to take a break of 10 minutes. Okay? So we will reconvene in 10 minutes time. Okay, so let us sort of reconvene after the 10 minutes and let us continue with the sort of the variations of the basic theme which we have been discussing, which is the following, that if you have, which is basically relating the following math fact. You can, there are multiple kinds of interest rates like simple interest rate and compound interest rates. Simple interest rates are given by a linear curve, a linear growth. Compound interest rates, on the other hand, are exponential curves or exponential growth, and the two are very different. In real life, we usually have compound interest rates, so we have to figure out ways to deal with this exponential growth. And we are dealing with that exponential growth using our master equation, which is Cn equal to 1 plus alpha to the n times C0. Okay? And basically, all that we are doing in various variations or examples on this theme is to play around with the various aspects of this idea. Okay? So, another question, another pertinent question is to sort of invert the point of view. So, we began with the point of view that we start with a certain amount of money, and in 2 years, and after a certain number of years, we want to know how much that has grown to if we operate under a given interest rate. Sometimes it might be of interest, particularly from the point of view of investments, as to determine the following question. So, suppose 20 years later, suppose after a certain number of years, for example, when I retire, I want to have a certain amount of money in my hand, and I will get that money by growing my own money now by investing it. I know the interest rate. So, I want to know for how much money I should invest now, so that after 20 years I get my desired amount of money then, okay, under the compound interest rate. So, my goal here is a little different. I am flexible on how much I can invest now, but my target is fixed. After 20 years, I want to have this particular amount of money under the given interest rate. Okay? So, it's kind of, so previously we had seen the forward problem, which is that I know I am given the amount of money I am investing now, and I want to know how much it will come to after 20 years. Here is the reverse problem. So, I have a target about how much I want to have after 20 years, and I want to reverse engineer it to calculate how much I should invest now. Okay? And again, it's a play on the same theme, it's a play on similar ideas. So, let's walk through it. So, generally speaking, what is having $x in k years? The rate of investment returns being I. So, if you want to have $x after k years with I % rate of interest, if you want to have $x after k years under rate of investment returns I, then how much should you invest now? So, this is the basic problem, right? So, here is a solution. So, again we use this equation Cn equal to 1 plus alpha to the n times C0. So, if you start with y dollars today, so C0 is y. After k years and investment return rate I, you will get Ck, which is 1 plus I to the k times C0, and C0 being y. So, this is 1 plus I to the k times y. Okay? So, your equation should be, so if you want x dollars after k years, under these circumstances, your x will be governed by the equation x equal to 1 plus I to the k times y. So, x in k years time is equivalent to y equal to 1 over 1 plus I to the k times x. So, if you want to have x dollars after k years, you have to invest 1 over 1 plus I to the k times x dollars today. So, this is just the reverse problem. So, this y in finances is called the present value of x in k years time assuming interest rate of I, another piece of jargon. So, so what is so here is a reviewing example for this idea. So, remember this equation. What is x dollars after k years is y dollars today, where x and y are related by this equation. So, suppose you are given, so suppose you have an investment scheme where you have certain interest rate I, a certain rate of investment returns I, and you know, at certain points of time in the future, you want to get back after T1 years, you want to get $S1, after T2 years you want to get $S2, etc. So, maybe you know, you are making investment with for your kids. So, when he graduates from high school, you want certain amount of money. When he graduates from college, you want certain amount of money from that scheme, etc. So, you know, these are definite time points in his life. So, definite years, definite epochs at which you want certain predetermined amounts of money. So, the question is how much should you invest today when your kid is born, okay. So, if you want SI amount of money after TI years, then at the rate of investment returns, at the annual rate of investment returns I, recall the equation from the previous page, your x is SI and your k is TI. So, then today you should invest 1 over 1 plus I to the TI times SI in order to get SI amount of money after TI years. So, if you want all these monies at these particular epochs of time, then today you should invest in total this amount of money, okay. And this brings us to the summation convention. So, you have this sum. This sum you can write in a neat fashion like this. So, what is this? So, if you have a sum of variables A1 plus A2 plus A3 plus A4 up to plus AN, then you can, so the generic variable here is AI. So, you are just summing AI from 1 to n. So, you can express this sum as in the form of this notation, this sigma I is equal to 1 to n. So, this is the limits 1 and n, and then you put the generic variable AI. So, this notation sigma I is equal to 1 to n AI exactly means this sum, okay. So, this is a neat math notation. So, for example, if you have summation k equal to 0 x to the power of k, then it is just 1 plus x squared plus up to x to the 12. And this is, if you remember, this is the geometric series with common ratio x, okay. So, let us now go into a mortgage problem. So, so let us consider a rather complicated problem in terms of mortgage. I mean, it might seem complicated, but in the end we will see that again using these similar ideas it is going to be very simple. So, suppose you borrowed $100,000 at 6% annual interest rate to be paid monthly over 25 years. How much is your monthly payment and how much do you owe after, in the middle, let us say after 15 years? So again, let us put it in general in terms of symbols, because it's usually easier to manipulate that way mathematically. So you have borrowed $C, so C is 100,000. Annual interest rate is I, so I is 6%, and it's being paid monthly over n years, so n is 25. So what is your monthly payment? R, okay? So again, your annual interest rate is I. Your annual interest rate is I. Your monthly payment is R. So your monthly payment will depend on your monthly interest rate. So now let us assume that the monthly interest rate is alpha, and let us relate alpha with I. So if you started with C0 at the beginning of the year, at the end of the year you have 1 plus alpha to the power of 12 times C0, if your compound monthly interest rate is alpha. But your annual interest rate is I, so this is also the same as 1 plus I times C0. And therefore, you get this relation 1 plus alpha to the 12 times 1 plus I. So this we have already seen a few times in this lecture. So in our case, if the annual interest rate is 6%, that means I is equal to 0.06. So here we know the right hand side, which is 1 plus 0.06, which is 1.06. And then you can solve for alpha from this equation using your calculator, and you will get that alpha is 0.004867. So this is the monthly interest rate. So now we want to go to the second part, which is the amount owed at the end of 6 months, or at the end of 15 years. So in particular, we want to understand after k months generally, and then you can put the values. So you start with C0, so this is C. So you want to find the amount Ck, which is owed at the end of k months. So after the end of 1 month, how much do you owe? So you have, so you should have paid 1 plus alpha to the C times C0, but actually you are paying R, which is your monthly submission and monthly payment. So after 1 month, you have this amount which you owe to the bank. At the end of the second month, you apply this same argument with C0 replaced by C1. So after the second month, you owe 1 plus alpha times C1 minus R. Okay? So you can simplify this, because C1 by the previous equation is 1 plus alpha times C0 minus R. So you put that here, you substitute C1 from the previous equation, and you get C times C0 times 1 plus alpha square. So C is the same as C0. So this is times 1 plus alpha square from this term, minus R times 1 plus alpha from this term, and then R. Okay? So now we can see where this is going. You can consider C3. This is 1 plus alpha times C2. This is what you owe at the end of the third month, deducted what you already paid to the bank in the third month, so deducted the monthly payment for the third month. And then you can put C2 equal to this equation, so C2 equal to C 1 plus alpha square minus R times 1 plus alpha minus R minus R. Okay? And generally you can continue like this. So Ck in general will be 1 plus alpha times Ck minus 1 minus the monthly payment R. So you can do this substitution at every step, and what you will get is that, so you can simplify this particular case as C times 1 plus alpha cubed minus R times 1 plus alpha squared minus R times 1 plus alpha minus R. Okay. So this is C3. So in general you can guess what is going to be Ck. Ck is going to be C0. So this is the initial amount, C0 times 1 plus alpha to the k, and minus R times 1 plus alpha to the various powers, from starting from 1 all the way up to the power k minus 1. So this is C, for example, this one is C0 1 plus alpha to the 3 minus R times 1 plus alpha square plus 1 plus alpha plus 1, right? So similarly, you can do this simplification for Ck by substituting Ck minus 1 here, and you will get something like this. So so this is C3. So this was C3 from the previous slide. So in C3 you have the power 3 here, right? For C3 you have the power 3 here. So for Ck you have the power k here. You have C0, and then you have R times the sum of the powers of 1 plus alpha, like this, starting from 1 all the way up to k minus 1. And in summation notation, it's exactly going to be this equation. And then this brings us to the next math fact. If you have a geometric series and you sum it like this, you can simplify it in this simple form. And why is it relevant for us? It's relevant for us because here we exactly have a geometric series like this with x equal to 1 plus alpha, right? So this series using this formula is nothing but this. So this is 1 minus x to the k, and x is 1 plus alpha. So 1 minus 1 plus alpha to the k divided by 1 minus 1 plus alpha. So this is equal to this. Okay. So so in other words, the amount of money you owe to the bank after k years is simply 1 plus alpha to the k times c, which was the first term here, minus r times the sum of this series, which is r times this one, which according to this formula is r times this factor. Okay. So this is what you owe after k months. So so what is our objective? So we want to set the rate of monthly payment to the bank so that after n years, which is n for us was 25 to begin with, I suppose. So after n years, you completely pay off the bank. So after n years, so n years means 12 n months. So we have done the calculation in terms of months, not years. So k is equal to 12n because you have n years. So this is 12n months. So here is what is happening. So every month, because of the monthly interest rate, you accrue some debt to the bank. But every year, every month, you are also paying back an amount of money which is R to the bank. Okay? So there is a competition between these two. On one hand, you are owing more money to the bank, but on the other hand, you are also paying them back at the rate R per month. So you want to adjust this R so that after 25 years, which is 12 times 25 months, your what you are paying with catches up with what you are owing to the bank. And here we had the formula of how much you owe to the bank after k months. So, you want to adjust R. So, here what do we know? We already know alpha, because alpha is 1 plus I to the 1 over 12, and so we already calculated it to be this 0.004, etc. So, alpha we know from the annual interest rate for the loan. C we know because that is the initial amount of loan we have taken. And so, we want to find k. So, we also know k, because k is the number of months we have in 25 years, because we want to pay the loan back in 25 years. So, k is also known. K is 12 times n, which is 12 times 25. So, in 12n months, we want the amount of money we owe to the bank, which is the amount of debt accumulated minus the amount of payments that we have, amount of monthly payments that we have made to the bank. We want our monthly payments to catch up with the total amount of accumulated debt. So, these two terms after 25 years should be the same, or rather R should be chosen so that these two terms are the same after 25 years. So, if these two terms are the same after k is equal to 12n months, or 12 times 25, k equal to 12 times 25 months, then these two terms being equal should mean that Ck is 0, right? So, they are equal, so their difference is 0. So, C of 12n is 0, where n equal to 25, okay, in our example. So, you put that, substitute that in this equation. So, 1 plus alpha to the 12n times C minus 1, this expression with k equal to 12n times R should be 0, okay. And then you simply solve this to get this complicated looking equation for R, but actually this equation is not very complicated, because if you put it in a calculator or in your computer, it will just do it in a jiffy. But the main idea is that using the very simple ideas or using the very simple themes of dealing with compound interest and these geometric series, we are able to calculate the amount of interest that we should repay, the amount of money that we should repay the bank every month, so that after 25 years, that is k equal to 12n is equal to 12 into 25 months, I am able to repay the bank fully, so that the amount of money I owe to the bank becomes 0, so that C times C of 12n is 0, and we can use this equation to get the value of R. Okay? So, so in particular, if you put the values, alpha is 0.004847, n equal to 25 years, I is equal to 0.06, and C equal to 100,000. You can do the calculation with your calculator here and come up with monthly repayment of $634.62, which looks pretty reasonable. Okay? So, the whole idea is that it might look like a really complicated real life problem of calculating the monthly payments, so that even with all these complications of compound interest, you are able to fully repay the bank after 25 years. But if you use these very simple mathematical ideas involving this accumulation of compound interest and geometric series, you can easily get the solution. Okay? So, this is what we have for today, and in the next lecture we will continue with discussion on personal finance and money.